Hello everyone, my name is Shang, a graduate student from School of Computer Science and Information Engineering at Hefei University of Technology. It's an honor to do the presentation. The title of my paper is Smart Contract Vulnerability Detection based on Dual Attention Graph Convolutional Network. Next, I will report the following aspects, including problem background, problem description, proposed method, experiment results, and conclusion. First, let me introduce the background of the problem. Blockchain has been applied to various fields like industry, healthcare, supply chain, and so on. The creation of smart contracts is a milestone in the history of blockchain. A smart contract, which can be seen as a program running on the blockchain system, can automatically perform the execution of transactions triggered by certain events. Once deployed on the blockchain, smart contracts are not allowed to be modified due to the decentralized, transparent, and immutable characteristics of blockchain. However, serious vulnerabilities in smart contracts can be utilized, leading to huge financial losses. In June 2016, a large crowdfunding organization deployed on Ethereum had $150 million worth of Ethereum digital currency stolen. In June 2017, Parity, a widely used digital wallet, was attacked, which directly resulted in a $30 million financial loss. Therefore, the smart contracts require strong security assurance, and there is an urgent need for effective vulnerability detection of smart contracts, such that we can remove the found vulnerabilities in the smart contracts before deploying them. For the detection of smart contract vulnerability, existing researches, mainly based on traditional methods such as symbolic execution or fuzzy detection. Some studies also use deep learning approaches via either sequence-based or graph-based feature representation model. However, adopting traditional methods in vulnerability detection demands expert definition of logic rules, which takes heavy reliance on experience, capability of professionality, and understanding of domain knowledge. The design process of logical rules can also consume significant time. Besides, the manually set rules are often limited to specific tasks and easily prone to errors. When it comes to the deep learning methods, neither sequence-based nor graph-based feature representation models in the existing work can fully retain the rich structural or semantic information in the smart contracts and learn high-dimensional features effectively for classification. Next, I will talk about the problem description. In this paper, we study how to detect whether a smart contract is vulnerable based on the smart contract bytecode. Specifically, we investigate two types of vulnerabilities, that is, reentrancy and timestamp dependency. Reentrancy is a vulnerability of great concern existing in Ethereum smart contracts. Here's an example showing a simplified real-world attack using reentrancy. There is a special mechanism in a smart contract system called fallback function, which has no function name and takes no arguments. The fallback function will be invoked in two scenarios: when the function call does not match any functions in the called smart contract, or the digital currency, Ether, is received by the caller. There are two contracts in the picture. Contract attacker attempts to steal the Ether from contract victim, a simplified version of digital wallet with a reentrancy vulnerability, by exploiting the fallback mechanism. To be specific, attacker executes its attack function to invoke withdraw function in victim. Victim will then transfer a certain amount of Ether to attacker, Once the ether is received, the fallback function in attacker will be executed. As we can see, the balance of attacker's account has not yet been set to 0 by victim at the time. The attacker can thus repeatedly invoke the withdrawal until the ether held by victim drops to 0. Timestamp dependency is another well-known Ethereum smart contract vulnerability, which is related to timestamp in the blockchain system. Here's a contract suffering from the timestamp dependency vulnerability. Contract the run in the picture uses a set of rules based on the current block timestamp to choose who will win the bonus. In this contract, the variable h defined in line 7 is the hash value of a certain block in the blockchain, which is used to decide the winner. The selection of a block is determined by the variable seed defined in line 6. 3 variables decide the seed value, including block number, last payout, and timestamp. Among them, block number and last payout are determined values recorded on the blockchain, while timestamp is decided by the miner. Normally, the timestamp is set as the current time of the miner's local system. However, the miner can vary the timestamp value by roughly 900 seconds, while still having other miners accept the block. Therefore, by choosing the timestamp, the miner can calculate the result in advance and manipulate the outcome of contracts to get the final bonus. Next, I will present our proposed method. To address the problem of smart contracts vulnerability identification, we propose a novel smart contracts vulnerability detection method. We first generate the attributes of smart contracts, including the control flow graphs and the Ethereum virtual machine opcode sequences. We then proposed a novel model, dual attention graph convolutional network, to detect vulnerabilities in smart contracts. To better express the rich semantic and structural information in smart contracts, we generate both control flow graphs and opcode sequences from smart contract bytecodes as attributes. Here's a picture illustrating the workflow of attributes generation from smart contract bytecode. First, we represent the smart contract bytecodes as CFGs. Every node in a CFG represents a basic block consisting of a sequence of opcodes. The basic blocks are independent of each other. That is, each basic block can only be entered as the first instruction and exited as the last instruction. 2 neighboring basic blocks are connected by a directed edge. In this graph structure, we put the basic blocks in the order in which they appear in the EVM bytecode. Among the complete 150 instruction set, we select totally 74 of them. Each can best reflect the logic and semantics of smart contracts execution process and relate to the smart contracts vulnerability detection tasks. We categorize the selected instructions into 7 types and take the numbers of instructions in different types as the attributes. Considering that CFGs working at the basic block level cannot capture certain finer-grained information, we further extract the opcode sequences in each basic block and concatenate them together in the same order as the basic blocks appears. Before feeding the opcode sequences into the neural network, we map each opcode to a unique integer. The DAGCN model shown in the picture consists of 3 modules: graph convolutional module, dual attention module, and classification module. In the graph convolutional module, we use graph convolutional layers at the control flow level to propagate each basic block's features to the neighbor blocks based on the structural connectivity, extract the features of the graphs, and then the structural information in the smart contracts. In this module, we use multiple stacked graph convolutional layers. Here's the propagation formula from the graph convolutional layer T to layer T plus 1. In this formula, F denotes the activation function, D and A denotes the degree matrix and adjacency matrix. ZT is the output of the Tth graph convolutional layer, and WT denotes the parameter matrix. In the dual attention module, we calculate the attention coefficients at the opcode level and control flow level, respectively. In the extraction of opcode level attention, we first apply word embedding so that the instructions mapped as different integers are transformed into fixed-size real-value vectors. To exploit the ordering information of the opcode sequence, the position of each instruction is encoded. The position encoding is then added to the embedding vector. The self-attention mechanism uses the scaled dot product attention to solve the long-distance dependency problem in long sequences. In the computation formula of traditional self-attention, I and J denotes the I's position and the J's position in an opcode sequence. Alpha I is the attention coefficients of position I. Q, K, and V are query, key, and value vectors at position I. D is the dimension of each vector of Q, K, and V. Pi denotes all the queries which the query at position I can attend to, and Z denotes the softmax function. However, the traditional self-attention mechanism will consume huge memory resources because of the multiply of QK matrix. So we adopt locally sensitive hashing self-attention mechanism to simplify the calculation. LSH is a hashing scheme that can find nearest neighbors quickly in a high-dimensional space, where nearby vectors get the same hash value with high probability and distant ones do not. In the LSH self-attention, we update PI by filtering the keys into different hash buckets using a locally sensitive hashing function H from the queries. Because of the number of keys and queries may not be balanced in different buckets, we further set K equals to Q. We then divided the sorted queries into several parts, each containing the same fixed number of queries. Obviously, the queries in the same buckets may fall into different parts. Therefore, we repeat NH rounds of the hashing process, each round with a different hash function HR, where R denotes the rth round of hash calculation. When it comes to the attention of control flow level, we focus on basic blocks that are more important for the vulnerability classification by assigning them greater weights. We take the CFG feature map obtained by performing all M graph convolutional layers on the control flow graphs as the input. We apply average pooling and max pooling on the channels of each node to better describe the relationship of different channels. Moreover, to better aggregate the attributes of each node and its neighboring node, we also apply a one-dimensional graph convolutional layer. The features extracted from the layers above are fed into a shared MLP with a hidden layer and then add together to calculate the attention coefficients on the control flow level. And then, in the classification model, we concatenate the features extracted from the graph convolutional model and dual attention module, and then perform classification via convolutional layer. max pooling, fully connected layer, and softmax function. Next, I'll discuss the experiment results. Our dataset integrates the real-world vulnerability smart contracts, including the dataset in Solidify, the dataset used in related papers, and smart contracts verified by smart bugs, targeting reentrancy and time-step dependency vulnerabilities. We further divide our dataset into training set, validation set, and test set. We evaluate our proposed model in terms of 4 performance metrics: accuracy, precision, recall, and F1 score. We compare the proposed model DAGCN with the state-of-art smart contract detection model TMP and the state-of-art deep learning models dealing with sequences or graph structures, including BiLSTM with attention, transformer, and DGCNN. As shown in the table, our model DAGCN achieves the best performance among the different methods. In the smart contracts vulnerability detection, both opcode sequence and control flows plays an important role in smart contract vulnerability detection. Separate analysis of contract flow graphs or opcode sequences may lose certain semantic and structural information. The proposed DAGCN model uses a hybrid model to jointly learn the control flow graph and opcode sequences features and improves the performance compared to the methods which only consider the features from either of the 2 levels. We also evaluate the effectiveness of each model using the receiver operating characteristic curve and the area under curve. It can be seen that the proposed model performs the best among the different models and achieves the AUC of 0.94 and 0.92 on the 2 vulnerability detection tasks, respectively. Finally, I'll make a brief conclusion. We tackle the problem of smart contract vulnerability identification based on smart contract bytecodes. We generate the attributes of smart contracts, including the control flow graphs and the EVM opcode sequences, and also proposed a dual attention graph convolutional network. We obtained the dataset from real-world Ethereum smart contracts containing 2 vulnerabilities, reentrancy and time-step dependency. Experimental results demonstrate that DAGCN could effectively improve the performance in terms of accuracy, precision, recall, and F1 score on smart contract vulnerability. That's all of my presentation, and thank you for listening.